What kills entire galaxies? Tonight, we're going to explore the most destructive machines ever discovered in our universe. You've probably heard the word quasar thousands of times in documentaries and science articles. But here's what most people don't realize. These aren't just bright lights in space. They're cosmic assassins that can sterilize regions millions of light years across, turning vibrant galaxy-forming regions into empty voids where nothing can ever live again. By the end of this journey, you're going to understand exactly why quasars represent the most terrifying and magnificent forces in cosmic history. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Let's begin. In the final days of the 1950s, radio astronomers working late shifts at observatories around the world began detecting signals from space that defied every explanation science could offer. These weren't the familiar radio whispers of known stars or the predictable patterns of planetary emissions. These were something entirely different. Picture yourself as one of those early researchers, hunched over primitive equipment in the cold darkness of an observatory. Your radio telescope picks up a signal so powerful, so impossibly bright, that your first instinct is to check if something went wrong with your instruments. But the signal persists, night after night, coming from the same tiny point in the sky. You're detecting radio waves more intense than anything you've ever measured. Yet when you point an optical telescope at that same location, you see nothing more than what appears to be an ordinary star. These mysterious radio sources appeared as simple points of light in the sky, visually indistinguishable from the countless stars you'd observed throughout your career. But their radio emission told a completely different story. They were pumping out radiation with an intensity that seemed mathematically impossible for any known type of star. It was like discovering that a candle flame could somehow illuminate an entire city. Your instruments weren't malfunctioning. Reality itself seemed to be breaking the rules. The objects were behaving like cosmic lighthouses, beaming signals across oceanic distances of space with a power that challenged the fundamental assumptions of astrophysics. These weren't nearby stars broadcasting weakly across short distances. The intensity suggested they were either relatively close objects with impossible energy output or distant objects with energy output so extreme it bordered on the supernatural. And as measurements improved, it became clear that the supernatural explanation was closer to the truth. Consider what this meant for the astronomers making these observations. You spend your entire career studying stars, learning their patterns, understanding their behavior. You know that a typical star emits a certain amount of radio energy based on its size, temperature, and age. These objects were violating every rule in the book. They were like finding a household flashlight that could outshine the searchlights of every airport on Earth combined. The term quasar emerged from the scientific community's honest confusion. Quasi-stellar radio source was simply an admission that astronomers literally could not identify what these objects were. They looked like stars through optical telescopes, but they behaved like nothing that had ever been catalogued. They were stellar imposters radiating energy on a scale that defied comprehension. The name itself was a placeholder, a scientific way of saying we have absolutely no idea what we're looking at. Imagine the moment of discovery compressed into human terms. You're walking through your neighborhood at night when you notice what looks like a normal streetlight in the distance, but as you approach it, you realize this streetlight is somehow illuminating not just the street, but the entire neighborhood, the whole city, and you can see its glow from the next county over. That sense of reality shifting beneath your feet was exactly what these early radio astronomers experienced. Everything they thought they knew about the universe suddenly seemed inadequate. The international astronomical community was in an uproar. Conferences that should have been routine gatherings of data presentation became heated debates about the fundamental nature of reality. Some astronomers suggested the observations were flawed. Others proposed entirely new physics. A few wondered if we were detecting artificial signals from advanced civilizations. The only thing everyone agreed on was that nothing in their textbooks could explain what they were seeing. The spectral analysis revealed the first hints of something truly extraordinary. Spectral lines are like fingerprints. They show exactly which chemical elements are present in a star or galaxy by revealing specific wavelengths of light that those elements absorb or emit. Every element has its signature, as reliable as a barcode, but the spectral lines from these objects were shifted toward the red end of the spectrum in ways that seemed to violate the known laws of physics. The redshift was so extreme that familiar elements appeared to be moving at speeds that should have been impossible. When Martin Schmidt first analyzed the spectrum of 3C273 in 1963, he spent weeks convinced he had made a calculation error. The numbers indicated that this object was receding from us at nearly 50,000 kilometers per second, about 16% the speed of light. At such velocities, the object would have to be billions of light-years away to produce the observed redshift. But if it was that distant and still visible from Earth, its energy output would have to be absolutely staggering. To understand the energy scale we're discussing, consider this comparison. If a typical star is equivalent to a 100-watt light bulb, the first quasars discovered were functioning like 25 trillion light bulbs, all blazing simultaneously from the same point in space, not spread across a galaxy, not distributed among millions of stars, but concentrated in a region smaller than you could see with the naked eye from Earth. Imagine trying to power 25 trillion light bulbs from a single electrical outlet, and you begin to understand the impossibility of what astronomers were observing. The numbers become even more staggering when we look at specific examples. The quasar designated 3C273 outputs 2.5 x 1040 watts of power continuously. To put this in perspective, that represents more energy than 25 trillion suns combined. And remember, our sun is already so powerful that it could evaporate every ocean on Earth in less than a second if it were moved close enough. This single quasar was outshining entire galactic neighborhoods. Here's a thought experiment to help you grasp this scale. If we could somehow relocate this quasar to a distance of 33 light-years from Earth, still much farther than our nearest stellar neighbor, it would appear in our sky with exactly the same brightness as our sun. A point of light 33 light-years away, matching the apparent brightness of the star that sits just 8 light minutes from our planet. You would need sunglasses to look at a star that's nearly 200 times farther away than the sun. These objects were performing the cosmic equivalent of an ant lifting an elephant. Single-point sources, no larger in appearance than stars, were generating luminosity equivalent to 100 entire galaxies like the Milky Way. Imagine trying to explain to someone that a grain of sand could somehow produce the same amount of light as a stadium full of floodlights, and you'll understand the conceptual challenge these discoveries presented. The energy density was so extreme, it seemed to mock the laws of physics. The theoretical breakthrough came in 1964 when astronomers Edwin Salpeter and Yakov Zeldovich proposed an explanation that would forever change our understanding of what was possible in the universe: supermassive black holes. These weren't the stellar mass black holes that form when massive stars collapse, but gravitational monsters millions or billions of times more massive than our sun. Objects so massive they could swallow entire star systems without changing their gravitational appetite. The idea was revolutionary and terrifying in equal measure. But even this explanation seemed inadequate at first. Black holes were theoretical constructs in 1964, mathematical solutions to Einstein's equations that most astronomers weren't sure actually existed in nature. Proposing that the most luminous objects in the universe were powered by the most invisible objects in the universe seemed like science fiction. Yet as the evidence mounted, this impossible explanation began to seem like the only possible one. One of the most puzzling aspects of quasars was their variability. These objects could change their brightness dramatically over periods of just hours or days. This variability provided a crucial clue about their true nature, because the speed at which something can change tells you something fundamental about its size. Light can only travel at 300,000 kilometers per second, so if an object doubles its brightness in 6 hours, the entire structure producing that brightness cannot be larger than 6 light hours across. Think about this constraint for a moment. These quasars were producing energy equivalent to hundreds of galaxies, but they were doing it from regions smaller than our solar system. It's like discovering that all the power generated by every electrical plant in your country is actually coming from a device no larger than a shoebox. The concentration of energy defied every intuitive understanding of how the universe operated. It was as if nature had found a way to compress the energy output of a small galaxy into a space that wouldn't fill the gap between Earth and Jupiter. The astronomical community struggled to accept these measurements. Surely there was an error somewhere, but independent observations from different telescopes around the world confirmed the same impossible results. The objects were real, they were incredibly distant, and they were more powerful than anything that should have been able to exist. The redshift measurements revealed perhaps the most mind-bending aspect of all. Redshift occurs when light waves are stretched as they travel through expanding space. The farther away an object is, the more its light is shifted toward longer, redder wavelengths. The redshift of many quasars indicated distances of billions of light years, meaning we were observing these objects as they existed when the universe was only a fraction of its current age. We were looking back through cosmic time to witness events that occurred in the universe's violent youth. This temporal aspect added another layer of mystery. If quasars were so common billions of years ago that we could detect them across vast cosmic distances, why weren't there any nearby examples? The closest quasars were still hundreds of millions of light years away. It was as if the universe had gone through a phase of incredible violence in its youth, then settled into the relative calm we observe in our local cosmic neighborhood. Between 1960 and 1963, astronomer Martin Schmidt achieved the first successful decoding of a quasar spectrum. His analysis revealed that 3C273 was located an almost incomprehensible 2.4 billion light-years from Earth. The light we were detecting had been traveling toward us for longer than complex life had existed on our planet. We were seeing ancient history written in electromagnetic radiation, witnessing events that occurred when the universe was barely a quarter of its current age. Schmidt later described the moment of realization as both thrilling and terrifying. He had spent months assuming his calculations were wrong, rechecking his work, looking for the error that would bring the numbers back into the realm of possibility. But the error never appeared. The object really was that distant, and it really was that powerful. The universe was revealing itself to be far stranger and more violent than anyone had imagined. To help you visualize the stellar comparison, consider this calculation. If you could count 1 star per second without stopping, you would need more than 32,000 years of continuous counting to tally all the stars that a single quasar outshines. That's longer than the entire history of human civilization, spent counting stars that collectively produce less light than one quasar. Every second of your counting would represent a star that contributes less light to the universe than 1/32,000th of 1 year's worth of quasar observation. These discoveries were like finding a candle flame visible from another continent. The energy requirements seemed to break fundamental rules about what was possible in nature. Yet there they were, detected night after night by independent observers around the world, undeniably real despite being theoretically impossible. The universe was operating machinery that exceeded our wildest engineering fantasies. Radio telescopes across different continents confirmed each other's observations, eliminating the possibility of instrumental error. The signals were coming from precise coordinates in space, repeating their impossible performance with clockwork regularity. Some quasars maintained their incredible brightness for months or years, while others flickered and varied like cosmic beacons, sending messages across billions of years of space and time. The discovery of quasars marked a watershed moment in human understanding. For the first time, we had encountered phenomena that genuinely transcended our previous conception of cosmic power. We had always known the universe was large, but quasars revealed it was also capable of violence and energy output on scales we had never imagined. They forced us to confront the possibility that our quiet corner of the cosmos might be an exception rather than the rule. For decades after their discovery, quasars remained the most mysterious and powerful objects ever detected. They represented the absolute limit of what nature seemed capable of producing, cosmic engines that pushed the laws of physics to their breaking point. Every measurement revealed new aspects of their impossible nature, each observation raising more questions than it answered. Teams of astronomers dedicated entire careers to understanding just one aspect of quasar behavior. The implications were staggering. If objects this powerful existed, what did that mean for our understanding of cosmic evolution? If the universe could produce energy concentrations this extreme, what other impossible phenomena might be lurking in the darkness between galaxies? The discovery of quasars opened a door to a universe far stranger and more dangerous than we had ever conceived. But this initial discovery was merely the first glimpse of a cosmic reality that would completely redefine our understanding of power, scale, and destruction in the universe. And as we would soon learn, the true significance of quasars extended far beyond their impressive energy output. They were not just the brightest objects in the cosmos, they were something far more ominous. They were cosmic assassins capable of sterilizing entire regions of space, transforming vibrant star-forming regions into barren voids where nothing could ever live again. To truly comprehend the devastating power of quasars, we first need to establish a hierarchy of the most destructive forces we know, starting right here on our own planet. Because until you understand what real destruction looks like on human scales, you cannot possibly grasp the cosmic violence we're about to explore. The most powerful nuclear explosions ever detonated by humanity release approximately 50 megatons of TNT equivalent, enough energy to vaporize an entire city in seconds. Picture your hometown, every building, every street, every living thing within its borders. Now imagine all of that matter converted instantly to superheated plasma and expanding shockwaves. That's the scale of destruction we're talking about when we discuss our most powerful weapons. The Soviet Union's Tsar bomba, detonated in 1961, created a fireball 8 kilometers in diameter, large enough to engulf Manhattan from the financial district to Central Park, like a bubble of pure energy expanding at supersonic speeds. This explosion generated a mushroom cloud that reached 64 kilometers into the atmosphere, breaching the boundary between Earth's atmosphere and space itself. The thermal radiation from this single detonation could have caused third-degree burns to observers 100 kilometers away. But even our most destructive weapons pale in comparison to the forces that Earth itself can unleash. Supervolcanoes, like the one beneath Yellowstone National Park, store energy equivalent to millions of nuclear bombs. These geological monsters are capable of altering global climate for decades through the sheer volume of ash and sulfur compounds they inject into the atmosphere. When they erupt, they don't just destroy local regions, they affect the entire planet's weather patterns. Consider the eruption of Mount Tambora in 1815. This Indonesian volcano released energy equivalent to 800 megatons of TNT, 16 times more powerful than the largest nuclear weapon ever detonated. The ash and sulfur dioxide it ejected into the atmosphere caused global temperatures to drop by up to 3 degrees Celsius, creating the year without a summer in 1816. Crops failed across Europe and North America, leading to widespread famine that killed hundreds of thousands of people. A single volcanic eruption in Indonesia caused starvation in New England. Earthquakes represent yet another level of terrestrial destruction. The magnitude 9.0 earthquake that struck Japan in 2011 released energy equivalent to 32 billion tons of TNT. To put this in perspective, that's more than 600 times the energy of the largest nuclear weapon ever built. This earthquake was so powerful it moved the main island of Japan 2.4 meters eastward and altered the length of Earth's day by 1.8 microseconds by changing the planet's moment of inertia. Think about that for a moment. The earthquake actually changed how fast our planet rotates. The redistribution of mass caused by moving continents affected the spin of an entire world. When geological forces can alter planetary rotation, you begin to understand that we live on a dynamic, violent planet that's constantly reshaping itself with energies that dwarf human technology. But even the most catastrophic earthquakes seem modest when we consider asteroid impacts. The asteroid that exterminated the dinosaurs 66 million years ago released energy equivalent to 100 trillion tons of TNT. That's roughly 10,000 times more energy than the largest earthquake ever recorded. Like a cosmic cannonball striking a soap bubble, this 10-kilometer-wide chunk of rock created a crater 180 kilometers in diameter and ejected molten material completely around the globe. The Chicxulub impact was so violent, it temporarily turned parts of Earth's surface into something resembling the hellish landscape of Venus. Rock was vaporized and ejected into space, some of it escaping Earth's gravity entirely. The energy was sufficient to melt and eject material equivalent to thousands of times the volume of the impactor itself. Debris rained down across the entire planet as a global firestorm that may have raised surface temperatures to over 300 degrees Celsius. Expanding our perspective to the solar system reveals forces that make terrestrial destruction seem almost quaint. Our sun continuously produces 3.8 x 1026 watts of energy, equivalent to 100 billion megatons of TNT detonating every second, without pause, for the past 4.6 billion years, and continuing for roughly 5 billion more years. To help you visualize this constant energy output, if you could capture just 1 second's worth of the sun's energy production, it would be equivalent to every nuclear weapon ever built by humanity detonating simultaneously. And the sun does this every second of every day, powered by nuclear fusion reactions that convert 600 million tons of hydrogen into helium each second, with 4 million tons of that mass converted directly into energy. Solar flares represent the sun's version of temper tantrums. And even these relatively minor outbursts can release energy equivalent to 10 billion hydrogen bombs in a matter of minutes. These eruptions generate magnetic storms that can disable electrical systems across entire planetary surfaces. The charged particles they hurl into space travel at speeds of up to 2,000 kilometers per second, carrying enough energy to strip away the atmospheres of unprotected planets. The Carrington event of 1859 demonstrated the sun's ability to affect technology even during the primitive electrical age of the 19th century. This solar storm was so powerful that telegraph operators received electric shocks from their equipment. Telegraph lines sparked and caught fire, and some telegraph systems continued operating without any external power source, running entirely on the electrical current induced by the magnetic storm. Aurora displays were visible as far south as the Caribbean. Imagine seeing the northern lights from Florida. Jupiter, our solar system's giant protector, demonstrates gravitational forces that routinely perform feats of cosmic destruction. With its immense mass, Jupiter acts like a cosmic vacuum cleaner, capturing comets and asteroids that might otherwise collide with inner planets. But Jupiter doesn't just capture these objects. It tears them apart with gravitational forces that exceed anything we can produce on Earth. The gravitational stress exerted by Jupiter is so intense that it shredded comet Shoemaker-Levy 9 into 21 separate fragments before those pieces ever reached the planet's atmosphere. Imagine forces so powerful they can tear apart a mountain-sized chunk of ice and rock simply through gravitational stress. Each fragment was like a cosmic bullet made of ice, rock, and dust, traveling at tens of thousands of kilometers per hour. When those fragments finally collided with Jupiter in 1994, each impact released energy equivalent to 6 trillion tons of TNT. The largest fragment alone produced an explosion 2,000 times more powerful than the global nuclear arsenal. These impacts created atmospheric scars larger in diameter than Earth itself. Dark spots that remained visible for months as monuments to the violence of planetary collisions. The impact sites appeared as dark bruises in Jupiter's atmosphere, each one representing a release of energy that could have sterilized Earth's surface. These weren't just explosions, they were cosmic catastrophes that temporarily heated Jupiter's atmosphere to temperatures exceeding 30,000 degrees Celsius, hot enough to break apart molecules and atoms themselves. The shockwaves from these impacts propagated around Jupiter's entire circumference, yet for all this demonstration of solar and planetary power, we're still dealing with forces that represent merely a drop of water compared to the cosmic violence that operates on galactic scales. Our Sun, with all its awesome nuclear fury, produces only 0.0001% of the energy that an average quasar emits continuously every second that passes. Let that fraction sink in for a moment. Take the most powerful force in our solar system, the engine that drives all weather, all life, all geological processes on Earth, and it represents 1/10,000,000th of the power output of a typical quasar. If our sun were a birthday candle flickering in the darkness, a quasar would be like having 25 trillion suns burning simultaneously in the same point of space, not spread across a galaxy, not distributed among millions of star systems, but concentrated into a region smaller than our solar system. It's like comparing a firefly to a blast furnace, except the scale difference is billions of times more extreme. This comparison begins to prepare us for comprehending phenomena that completely transcend all scales of power known in human experience. We're about to explore forces that make solar flares look like static electricity and asteroid impacts seem like gentle raindrops. Every example of destruction we've discussed so far, nuclear weapons, supervolcanoes, earthquakes, asteroid impacts, solar storms, planetary collisions, collectively represents less energy than a quasar produces in the time it takes you to blink your eyes. Like ants attempting to observe a hurricane, our terrestrial perspective can barely begin to process the magnitude of forces that govern the cosmos at its most extreme scales. Our brains simply didn't evolve to comprehend energy outputs that exceed entire star systems. The numbers become so large, they lose meaning, like trying to count grains of sand by numbering each individual particle on every beach on Earth. Consider this progression: a nuclear weapon that can destroy a city, a volcano that can alter global climate, an earthquake that can move continents, an asteroid that can exterminate entire species, a star that can power biological evolution for billions of years. Each step up represents roughly a million-fold increase in energy, yet quasars operate at energy levels another trillion times beyond stellar output. We've climbed a ladder of destruction from human-scale violence to planetary catastrophes to stellar forces. Each rung seemed impossibly high from the previous level, yet we've only just reached the bottom rung of cosmic violence. The journey from terrestrial destructive forces to quasars represents a leap in scale so dramatic, it's like comparing a single spark to the explosion of a supernova. The forces we've catalogued so far, impressive as they seem from our human perspective, are about to be revealed as cosmically insignificant. We're preparing to enter a realm where individual objects can outshine billions of stars, where energy concentrations can sterilize entire regions of space, and where destruction operates on scales that challenge our fundamental understanding of what's possible in the universe. But before we can comprehend how quasars became the ultimate cosmic destroyers, we must first understand what happens when even the most massive stars reach the end of their lives. Even the most massive and violent stars in our galactic neighborhood seem insignificant when we begin exploring the true energy giants of the cosmos. Yet these stellar monsters provide the stepping stones we need to understand forces that will eventually dwarf them entirely. Let's start with stars so large they challenge our ability to visualize scale. Hypergiant stars like VY Canis Majoris possess radii 400 times larger than our Sun. If this stellar monster were placed at the center of our solar system, its surface would extend all the way to Saturn's orbit. Picture our entire planetary neighborhood, from Mercury to Saturn, completely engulfed within a single star's atmosphere. You could fit 2.7 billion suns inside this one stellar giant. Yet it still represents just one star among trillions in our galaxy. Like a basketball inflated to the size of a football stadium, these monstrous stars burn nuclear fuel at such extreme rates they consume in a few thousand years what our sun will spend over billions of years. They live fast and die young, burning through their nuclear reserves with the cosmic equivalent of a Ferrari engine running at maximum throttle continuously. A star that could power civilizations for eons instead chooses to burn brilliantly for a cosmic instant. When stars with more than 25 solar masses reach the end of their lives, they explode in supernovas that release more energy in 10 seconds than the sun will produce during its entire 10 billion-year existence. Imagine compressing the sun's entire lifetime energy output into a brief, cosmic hiccup. The violence is so extreme, it temporarily outshines entire galaxies containing hundreds of billions of stars. A typical Type II supernova emits 1044 joules of energy, equivalent to 100 trillion Hiroshima bombs detonating simultaneously in the same location. To put this in perspective, if every person on Earth possessed a nuclear arsenal equal to the combined weapons of all nations, and everyone detonated their entire stockpile at once, the result would still be millions of times weaker than a single supernova explosion. The brightness scale is equally staggering. If a supernova occurred just 25 light-years from Earth, still farther than our nearest stellar neighbor, It would shine in our sky with the same brightness as a full moon. You could read a book by supernova light. It would be visible during daytime for several consecutive weeks, hanging in the sky like a second sun that gradually faded over months. The 1987 supernova in the Large Magellanic Cloud demonstrated just how far-reaching these stellar explosions can be. This supernova, located 160,000 light-years away, released more energy in neutrinos alone than our entire galaxy produces in visible light during a complete year. Neutrino detectors on Earth registered particles that had traveled across intergalactic space, carrying energy from an explosion that occurred before human civilization began. The core collapse during a supernova creates conditions so extreme they mock our understanding of matter, like a cosmic hammer striking an iron anvil. The collapsing stellar core generates pressures so intense that protons and electrons, particles that normally repel each other, are forced to merge into neutrons. The atomic structure of matter breaks down under gravitational forces that compress entire mountain ranges into volumes smaller than cities. The resulting neutron stars have densities so extreme that a single teaspoon of their material would weigh approximately 6 billion tons. That's equivalent to compressing an entire mountain range into a coffee spoon. The surface gravity is so intense that if you could somehow stand on a neutron star, you would weigh 200 billion times more than you do on Earth. A fall from 1 millimeter height would generate the kinetic energy of a bomb explosion. Pulsars represent neutron stars taken to even greater extremes. These stellar remnants can rotate up to 716 times per second while sweeping space with radiation beams more precise than atomic clocks. Imagine something with the mass of our Sun, compressed into a sphere the size of Manhattan, spinning faster than a kitchen blender while emitting lighthouse beams that can be detected across thousands of light years. The rotational energy of these spinning neutron stars is staggering. QUASAR J1748-2446 the fastest spinning pulsar known, completes one full rotation every 1.4 milliseconds. Its equatorial surface moves at roughly 25% the speed of light, fast enough that relativistic effects begin warping space and time around the star itself. If this pulsar slowed by even a few microseconds per day, it would release energy equivalent to humanity's total annual power consumption. But supernovas represent merely the standard model of stellar death. Hypernovas are stellar explosions 100 times more powerful than normal supernovas, releasing 1046 joules and creating jets of material that travel at 99.99% the speed of light. These represent the death throes of the most massive stars in the universe. Objects so large they make our hypergiant examples seem modest by comparison. Hypernova jets punch through space like cosmic bullets fired from stellar cannons. The relativistic speeds involved mean these jets carry kinetic energy equivalent to converting entire planetary masses into pure energy. When aimed toward Earth, a hypernova occurring within our galaxy could deliver enough gamma radiation to strip away our ozone layer and trigger a mass extinction event. Even from distances of thousands of light years, when two neutron stars collide, they generate kilonovas, explosions that produce more gold and platinum in seconds than our Sun could manufacture during trillions of years of nuclear fusion. These cosmic forges create heavy elements through rapid neutron capture processes impossible to replicate elsewhere in the universe. The gold in your jewelry, the platinum in catalytic converters, the rare earth elements in your electronics. Much of this material was forged in the violent collision of stellar corpses. The neutron star collision designated GW170817 released gravitational energy equivalent to 3.5 solar masses converted completely into pure energy. This collision created ripples in space-time itself that propagated across the cosmos at light speed, carrying information about the most violent event witnessed in our cosmic neighborhood. The gravitational waves reached Earth 130 million years after the collision occurred, delivering news of ancient cosmic violence. Magnetars represent perhaps the most extreme stellar objects, short of black holes themselves. These are neutron stars with magnetic fields, trillions of times stronger than Earth's, capable of disintegrating atoms and generating stellar earthquakes that release more energy in 0.1 second than our Sun produces in 100,000 years. Their magnetic fields are so intense they warp the quantum vacuum itself, creating conditions that exist nowhere else in the known universe. If a magnetar were positioned halfway between Earth and the Moon, it would instantly erase every magnetic strip on every credit card, hard drive, and electronic device on our planet, but the magnetic effects would be the least of our problems. The radiation burst from such proximity would fatally interfere with the biochemistry of every living organism on Earth. The magnetar's field would be strong enough to levitate dire magnetic materials like water, wood, and even living tissue. Wolf-Rayet stars demonstrate stellar violence through continuous mass loss rather than sudden explosion. Stars like WR104 shed material through stellar winds so powerful they eject mass equivalent to our entire Earth every 100,000 years. Like a cosmic garden hose spraying sand instead of water, these stellar winds travel at velocities of 3,000 kilometers per second, creating spectacular spiral nebulae as the material interacts with the interstellar medium. The mass loss rates are so extreme, they fundamentally alter the surrounding space environment. Wolf-Rayet winds carry more kinetic energy than the orbital energy of entire planetary systems. They carve cavities in the interstellar medium hundreds of light-years across, creating cosmic bubbles where star formation is either enhanced by compressed gas boundaries or completely prevented by the removal of raw materials. Yet even these extreme stellar phenomena represent only localized events, affecting regions of a few hundred light-years around their positions in space. A supernova might sterilize nearby star systems and trigger star formation in compressed gas clouds. But its direct effects remain confined to its immediate stellar neighborhood. The influence, however catastrophic locally, falls off rapidly with distance. Consider the energy comparison that puts stellar explosions in cosmic perspective. The total energy of a supernova, devastating as it appears, is still approximately 100,000 times smaller than the energy a typical quasar emits during just 1 year of activity. It's like comparing a lightning strike to the continuous output of a power plant, impressive in its intensity, but dwarfed by sustained energy production. Even hypernovas, representing the most violent single events in stellar evolution, pale next to the sustained energy output of active galactic nuclei. A hypernova releases all its energy in a brief, explosive burst, while quasars maintain energy outputs millions of times greater continuously for millions of years. The stellar explosions we've discussed are cosmic firecrackers compared to the nuclear furnaces we're about to encounter. The patterns emerging from stellar evolution reveal a cosmic hierarchy of violence. Individual stars, no matter how massive, represent isolated events in space and time. Their explosions, however spectacular, affect only their immediate cosmic neighborhoods before fading into stellar remnants or black holes. But these stellar endpoints, particularly the black holes formed by the most massive stars, serve as the seeds for phenomena far more destructive than their stellar progenitors. Wolf-Rayet winds, supernova explosions, neutron star collisions, and hypernova jets all demonstrate that individual stars can achieve remarkable feats of cosmic violence. Yet they remain fundamentally limited by their initial stellar masses and the finite nuclear fuel available for energy production. They burn bright, explode magnificently, and then fade into comparative obscurity as white dwarfs, neutron stars, or black holes. We're only scratching the surface of the true cosmic monsters. Everything we've explored so far, hypergiant stars, supernovas, hypernovas, neutron star collisions, magnetars with their trillion Tesla magnetic fields, represents individual stellar phenomena operating on local scales. We're preparing to understand forces that operate on galactic scales and can influence the destiny of billions of stars simultaneously. The journey from stellar violence to galactic destruction represents another enormous leap in scale and sustained power output. While stars exhaust their fuel and die, while supernovas fade and neutron stars cool, the cosmic engines we're approaching next operate continuously for millions of years. Fed not by nuclear fusion, but by gravitational forces so intense they can tear apart the fabric of space-time itself. These stellar catastrophes serve as mere stepping stones toward comprehending objects that can devour stars like snacks, that can outshine entire galaxies for millions of years, and that can sterilize cosmic regions larger than the spaces between galactic clusters. Black holes represent the most extreme manifestation of gravity in the universe, where the very structure of space-time curves so radically that not even light can escape their gravitational embrace. They are the ultimate cosmic predators, lurking in the darkness of space with appetites that can never be satisfied. A typical stellar black hole, formed from the collapse of a star with 20 solar masses, possesses an event horizon just 60 kilometers in diameter, smaller than many terrestrial cities. Picture the entire mass of 20 suns compressed into a sphere you could drive across in less than an hour. Yet this seemingly modest object warps space-time so severely that it creates a point of no return from which nothing can ever emerge. Like a cosmic vacuum cleaner that devours everything in its path, the gravitational force near the event horizon is so intense that time literally slows down relative to the rest of the universe. This isn't science fiction. It's a measurable consequence of Einstein's general relativity. Clocks run slower in stronger gravitational fields, and near a black hole, this effect becomes extreme enough to stretch seconds into eternities for distant observers. If you fell toward a black hole, distant observers would watch you slow down, freeze in time, and gradually fade from view as your light became increasingly red-shifted. But from your perspective, you would experience something far more violent. The tidal forces, the difference in gravitational pull between your head and feet, would stretch you into a long, thin strand in a process astronomers grimly call spaghettification. You would be torn apart at the atomic level before ever reaching the event horizon. But stellar mass black holes are cosmic lightweights compared to the supermassive monsters that lurk at the centers of galaxies. Sagittarius A. The supermassive black hole at the heart of our Milky Way contains 4 million times the mass of our Sun, compressed into a volume smaller than Mercury's orbit around the Sun. Imagine the mass of 4 million suns crammed into a space that light takes just 8 minutes to cross. The gravity of Sgr-Eus is so intense that nearby stars orbit at velocities reaching 7,000 kilometers per second. That's more than 2% the speed of light. These stars complete elliptical orbits in just 16 years, racing around the black hole like cosmic Formula One cars on a track, measured in astronomical units rather than kilometers. The fastest of these stars experiences gravitational acceleration 25,000 times stronger than Earth's pull on objects at its surface, like marbles spinning around a basketball moving at hypersonic speeds. These stars experience relativistic effects that distort their orbits exactly as Einstein predicted. Their paths precess, gradually rotate, as space-time itself is dragged along by the spinning black hole. We can literally watch Einstein's equations play out in real time as these stars trace paths that would be impossible under Newtonian physics alone. In 2020, astronomers observed the star designated S2 Pass within 120 astronomical units of SGR-A, closer than the distance from the Sun to Pluto. During its closest approach, this star experienced gravitational acceleration 25. 0 times stronger than Earth feels from the Sun, while traveling at nearly 3% the speed of light. The precision of our measurements allowed us to confirm relativistic effects that had been theoretical predictions just decades earlier. Supermassive black holes can achieve masses that strain comprehension. TON 618, one of the most massive black holes known, contains 66 billion solar masses with an event horizon diameter of 600 astronomical units, larger than Neptune's orbit around our Sun. If our entire solar system were swallowed by TON 618, the volume occupied by all our planets would fit inside its event horizon more than 11,000 times over. Think about that scale for a moment. You could place 11,000 complete solar systems side by side within the event horizon of this single black hole. Our Sun, all our planets, the asteroid belt, Kuiper belt objects. Even the distant Oort cloud would represent less than 1/10,000th of the space inside this gravitational monster. It's like comparing a grain of sand to a sports stadium. When material falls toward a black hole, it doesn't simply disappear quietly into the darkness. Instead, it forms an accretion disk where gravitational friction heats gas to temperatures exceeding 100 million degrees Celsius, far hotter than the core of our Sun. This superheated material glows with such intensity it can outshine the combined light of billions of stars. Like a cosmic pressure cooker operating at infernal temperatures, these accretion disks emit X-rays so intense they can be detected across entire galaxies. The X-ray emission from SGR reaches Earth despite traveling 26,000 light-years through the dusty disk of the Milky Way. During active feeding episodes, the X-ray output can increase by factors of hundreds or thousands, briefly illuminating gas clouds throughout the galactic center. Paradoxically, black holes achieve energy conversion efficiencies that make stellar fusion look wasteful. While nuclear fusion in stars converts only 0.7% of mass into energy, black holes can convert between 5.7% and 32% of infalling matter directly into radiated energy. This efficiency approaches the theoretical maximum possible under the laws of physics. Black holes are the most efficient engines in the known universe. The mechanism behind this efficiency involves the rotation of space-time itself. A spinning black hole drags the fabric of space around with it in a phenomenon called frame dragging. Material in the innermost stable orbit experiences such extreme conditions that a significant fraction of its mass energy can be extracted before it crosses the event horizon. It's like squeezing every possible joule of energy from matter before it disappears forever. Relativistic jets emerge from the polar regions of spinning black holes, accelerating particles to 99.9% the speed of light and extending thousands of light-years into intergalactic space. These jets represent some of the most powerful phenomena in the universe, carrying more energy than the combined nuclear output of millions of stars. They punch through galactic halos and continue propagating through the vast emptiness between galaxies. Like cosmic cannons firing bullets of superheated plasma, these jets carry energy equivalent to trillions of stellar explosions. The jet from the black hole in galaxy M87 extends for 5,000 light-years, equivalent to 30 trillion kilometers of continuous high-energy beam. This single structure contains enough energy to power every star in a galaxy like the Milky Way for thousands of years. The particles in these jets move so close to light speed that relativistic effects become dominant. From our perspective, the jets appear to move faster than light due to projection effects, but the particles are actually traveling at 99.9% of light speed directly toward us. The kinetic energy carried by these relativistic particles exceeds the gravitational binding energy of entire star clusters. When supermassive black holes merge, they create gravitational waves that ripple through the fabric of space-time itself. The collision of two black holes, each containing billions of solar masses, converts roughly 8 solar masses directly into gravitational wave energy in a matter of seconds. This represents more power than the electromagnetic output of every star and galaxy in the observable universe combined. These gravitational waves propagate at light speed, carrying information about the most violent events possible in the universe. The waves stretch and compress space itself as they pass, distorting distances by amounts smaller than 1/10,000th the width of a proton. Yet our LIGO detectors can measure these minuscule changes, allowing us to witness cosmic collisions that occurred billions of years ago in distant corners of the universe. The merger of supermassive black holes represents the ultimate cosmic catastrophe. When two galaxies collide and their central black holes eventually spiral together, the final moments release more energy in gravitational waves than all the stars in both galaxies produce in electromagnetic radiation. It's the cosmic equivalent of converting several suns' worth of matter directly into ripples in the fundamental structure of reality. Black hole mergers also kick the resulting supermassive black hole out of its galaxy with velocities reaching thousands of kilometers per second. These rogue black holes career through intergalactic space, carrying with them the gravitational potential to disrupt any stellar systems they encounter. Some may wander the cosmic void for billions of years before being captured by another galaxy's gravitational field. The detection of gravitational waves has opened an entirely new window into cosmic violence. Events that were previously invisible, black hole mergers produce no light, no X-rays, no radio waves, suddenly became observable through their effects on space-time geometry. We can now witness the universe's most energetic events even when they occur in the darkest corners of space. Binary black hole systems spiral inward over millions of years, gradually losing orbital energy to gravitational wave radiation. The final merger happens incredibly quickly. The last few orbits take only milliseconds, during which the black holes complete several revolutions while traveling at significant fractions of light speed. The gravitational field changes so rapidly, it literally shakes the foundations of space and time. Yet even these phenomena of supermassive black holes, extreme as they are, still represent only the engine that powers something far more powerful and destructive. A sleeping black hole, no matter how massive, affects only its immediate gravitational neighborhood. But when these cosmic monsters begin feeding voraciously on the gas and stars around them, they transform into something far more ominous. The true manifestation of cosmic power occurs when supermassive black holes enter their active feeding phase, creating energy machines that can outshine entire galaxies and alter the destiny of billions of worlds. What we've explored so far, the warping of space-time, the acceleration of matter to near-light speeds, the conversion of mass to pure energy, these are merely the mechanisms that power the universe's most destructive forces. When a supermassive black hole awakens from dormancy and begins consuming material at maximum rate, it becomes something that transcends our definition of stellar phenomena entirely. Active galactic nuclei represent the crucial transition between dormant supermassive black holes and the most powerful destructive machines known in the observable universe. These are not the quiet, invisible gravitational monsters we've been discussing, but rather cosmic furnaces that have awakened to feed voraciously on the material around them. Approximately 10% of all galaxies in the universe host active nuclei, where central black holes consume material at rates equivalent to several solar masses per year. Imagine a black hole devouring multiple suns annually, converting that stellar mass into energy with an efficiency that makes nuclear fusion seem wasteful. This isn't occasional snacking. It's sustained cosmic gluttony operating on scales that challenge our understanding of energy production. Like cosmic blast furnaces operating in overload mode, these galactic nuclei convert the matter they devour into radiation with energy efficiency 40 times superior to the nuclear fusion processes that power stars. While stellar cores convert only 0.7% of hydrogen mass into energy. Active galactic nuclei can extract up to 32% of infalling mass as pure radiated energy. They represent the universe's most efficient energy conversion mechanisms. The discovery of these cosmic powerhouses began in 1943, when astronomer Carl Seifert identified galaxies with extraordinarily bright nuclei. Seifert galaxies revealed galactic centers that outshone their surrounding stellar populations by enormous factors, concentrated into regions smaller than our solar system. These were the first glimpses of what happens when supermassive black holes transition from dormancy to active feeding. NGC 1068, a Seifert galaxy located 47 million light-years from Earth, demonstrates the staggering energy output of active nuclei. Its central region emits more radiation than 100 billion stars combined. Yet this energy originates from a zone smaller than the distance between our Sun and Neptune. Picture the combined light of every star in a galaxy, like the Milky Way, concentrated into a space you could cross in a few hours at light speed. Radio galaxies like Cygnus A reveal even more dramatic manifestations of active galactic nuclei. These cosmic monsters produce lobes of superheated plasma extending 600,000 light-years from each side of the central galaxy, creating structures larger than several Milky Way galaxies placed end to end. The scale is so vast that light takes 2 million years to travel from one end of the structure to the other. Like cosmic balloons inflated by jets of relativistic particles, these radio lobes contain energy equivalent to 1058 joules. To put this number in perspective, this represents enough energy to power all of human civilization for trillions upon trillions of years. The total energy content of these structures exceeds the gravitational binding energy of entire galaxy clusters. The radio lobes aren't just static structures, they're dynamic systems where supersonic jets from the central black hole inflate vast cavities in the intergalactic medium. These jets travel at nearly the speed of light for hundreds of thousands of years, carving channels through space and depositing energy across cosmic distances. The process creates shock fronts that heat intergalactic gas to temperatures exceeding 100 million degrees. Blazars represent perhaps the most dramatic view of active galactic nuclei, appearing as cosmic lighthouses whose beams point directly toward Earth. When we observe a blazar, we're looking straight down the barrel of a relativistic jet, moving at 99.9% the speed of light. The beaming effect makes these objects appear incredibly bright and causes them to vary dramatically in brightness over remarkably short timescales. The blazar, designated 3C454.3, located an astounding 7.2 billion light-years away, has been observed increasing its brightness by a factor of 16 in just 36 hours. This variation represents an energy release equivalent to trillions of supernovas. Yet it occurs from a region that light can cross in less than 2 days. The energy density required for such rapid variability approaches the theoretical limits of what's possible in the universe. This extreme variability reveals something profound about the nature of these objects. Regions no larger than our solar system are somehow producing luminosity superior to entire galaxies containing 400 billion stars. It's like discovering that a single city block can outshine every light source across multiple continents, maintaining this impossible brightness for millions of years. Hubble Space Telescope observations have revealed that active galactic nuclei produce winds of ionized material traveling at velocities up to 20,000 kilometers per second. These aren't gentle stellar breezes, but cosmic hurricanes blowing through intergalactic space with enough kinetic energy to strip atmospheres from planets thousands of light years away. The mass loss rates approach 100 solar masses per year, equivalent to ejecting an entire star's worth of material annually. Like hurricanes on a cosmic scale, these galactic winds redistribute material across thousands of light years. They carry heavy elements forged in the nuclear cores of generations of stars, spreading these materials throughout galactic halos and into intergalactic space. The winds are so powerful they can permanently alter the chemical composition of entire galactic regions. Spectroscopic analysis reveals gas clouds moving at velocities up to 10,000 kilometers per second in the vicinity of active nuclei. These extreme velocities create turbulence that shreds molecular clouds and prevents new star formation across vast regions. The gravitational influence of the central black hole, combined with the radiation pressure from the accretion disk, creates a cosmic storm that can persist for millions of years. The broad line region surrounding active nuclei extends for dozens of light years and contains as much material as 10 million stars. This entire region orbits chaotically around the central black hole, with clouds of gas following complex trajectories in the intense gravitational field. The orbital velocities are so extreme that relativistic effects become significant, causing the observed spectral lines to be dramatically broadened by Doppler shifts. Active galactic nuclei emit radiation across the entire electromagnetic spectrum simultaneously. From low-energy radio waves to high-energy gamma rays capable of destroying organic molecules at distances of thousands of light years. This broad-spectrum emission indicates multiple physical processes operating simultaneously: synchrotron radiation from relativistic electrons, thermal emission from hot accretion disks, and inverse Compton scattering in the relativistic jets. The corona surrounding these accretion disks reaches temperatures of 100 million degrees Kelvin. In this extreme environment, free electrons collide with lower energy photons and boost them to X-ray energies through inverse Compton scattering. The temperature is so extreme that thermal motion of electrons approaches significant fractions of light speed, requiring relativistic corrections to basic physical calculations. X-ray mapping reveals that radiation from active galactic nuclei can ionize hydrogen in gas clouds located up to 100,000 light-years from the galactic center. This ionizing radiation is so intense it can penetrate the entire galactic disk and extend into the galactic halo, creating vast regions where normal chemistry becomes impossible. The radiation field is strong enough to dissociate molecular hydrogen and prevent the formation of new stars across enormous volumes of space. Like cosmic power plants operating without interruption, active galactic nuclei maintain constant energy output for millions of years. Unlike stellar explosions that release energy in brief bursts, These objects provide sustained power output that can exceed the luminosity of entire galaxies for geological timescales. They represent the most persistent and powerful energy sources in the known universe. The longevity of active galactic nuclei means they fundamentally alter the chemical structure of their host galaxies. Over millions of years of activity, they inject enough energy into the surrounding medium to heat gas to temperatures where it cannot cool and condense into stars. They also enrich the intergalactic medium with heavy elements, distributing the products of stellar nucleosynthesis across cosmic distances. Theoretical models suggest that every galaxy went through an active phase during its early evolution. The period of maximum quasar activity occurred when the universe was between 1 and 3 billion years old. Coinciding with the era when galaxy formation was most active, this suggests that active galactic nuclei played a crucial role in regulating cosmic star formation and determining the final properties of mature galaxies. The feedback mechanisms operate on multiple scales simultaneously. Locally, radiation pressure and relativistic jets clear material from the immediate vicinity of the black hole. Regionally, galactic winds remove gas from star-forming regions throughout the galactic disk. Globally, the energy injection heats the circumgalactic medium and reduces the rate at which new material can accrete onto the galaxy. Yet all these phenomena of active galactic nuclei represent only moderate versions of a specific type of object that elevates this power to absolutely devastating extremes. What we've explored represents the middle range of active galactic nuclei, impressive by any stellar standard, but still operating at energy levels that pale compared to the universe's most extreme manifestations. The most powerful active galactic nuclei operate at the absolute limits of what physics allows. They represent black holes feeding at maximum possible rates while spinning at near maximum velocities and generating magnetic fields of extraordinary intensity. When all these factors align, they create objects that transcend even our expanded definition of cosmic violence. When supermassive black holes achieve extreme feeding rates under specific conditions of rotation and magnetic field strength, they transform into the most powerful destructive machines in the cosmos, quasars. These are not merely bright lights in space, but cosmic assassins capable of sterilizing entire regions of the universe and preventing galaxy formation across volumes larger than galactic superclusters. Quasars represent the most energetic and destructive phase in the life of active galactic nuclei, occurring when supermassive black holes feed so voraciously they become visible across the entire observable universe. They are cosmic engines operating at the absolute limits of what physics allows, converting matter into energy with an efficiency that approaches theoretical maximums, while maintaining this impossible output for millions of years. The quasar J05294351, discovered in 2024, demonstrates the staggering scale of these cosmic monsters. This object contains a supermassive black hole with 17 billion solar masses that devours the equivalent of an entire sun every single day. Think about that rate of consumption. Every 24 hours, this black hole consumes more mass than our entire solar system contains, converting a significant fraction of that matter directly into radiated energy. Like a cosmic blast furnace operating in hypersonic nuclear fusion mode, this quasar emits 500 trillion times more energy than our sun. To put this number in perspective, our sun already produces enough energy every second to power human civilization for millions of years. This quasar produces 500 trillion times that amount continuously, day after day, for millions of years without pause. The accretion disk of this monstrous quasar measures 7 light-years in diameter. That's equivalent to 15,000 times the distance from our sun to Neptune, making it the largest accretion disk known in the universe. This single structure is larger than the distance to our nearest stellar neighbors. Yet it represents merely the feeding mechanism for an object that fits within what we would consider our local cosmic neighborhood. If this quasar were somehow relocated to the center of our galaxy, replacing our relatively quiet Sagittarius A, the radiation would be so intense that every ocean on Earth would vaporize in just 1/5 of a second. Not boil, not evaporate gradually, instantly convert to superheated steam from radiation pressure alone. The entire biosphere would be sterilized before you could finish reading this sentence. Typical quasars produce luminosities ranging from 1040 to 1047 watts, spanning from 25 trillion to 25 trillion times the power output of our Sun. Even the weakest quasars outshine our Sun by factors that require scientific notation to express. The most powerful quasars produce energy equivalent to the combined output of thousands of galaxies like the Milky Way, like cosmic lighthouses burning through the darkness of intergalactic space. Quasars can be detected at distances exceeding 13 billion light-years. We observe them as they existed when the universe was less than 1 billion years old. During the cosmic epoch, when the first galaxies were still forming, their light has been traveling toward us for longer than our solar system has existed. The quasar J0313-1806 pushes this temporal boundary even further. We observe this object as it existed when the universe was only 670 million years old, just 5% of its current age. This revelation tells us that supermassive black holes containing billions of solar masses already existed during the cosmic dawn, when the universe was still emerging from its dark ages. If cosmic history were compressed into a single year, we would be observing this quasar as it appeared in late January. The fact that such massive black holes existed so early in cosmic history suggests that the universe's violent phase began almost immediately after the first stars formed. There was barely time for a single generation of massive stars to live and die before these cosmic monsters were already feeding voraciously. The energy conversion efficiency of quasars is absolutely staggering. They can convert between 5.7% and 32% of infalling mass directly into energy, exceeding the efficiency of stellar nuclear fusion by factors of 45 or more. This approaches the theoretical maximum efficiency possible under general relativity. Quasars operate closer to physical limits than any other natural phenomenon. For every kilogram of matter that falls into a quasar's black hole, up to 320 grams can be converted into pure energy, according to Einstein's equation, E=mc². This releases approximately 29 trillion joules per gram of converted matter. To visualize this energy density, converting just one paperclip's worth of matter would release energy equivalent to the Hiroshima bomb. The relativistic jets produced by quasars extend for hundreds of thousands of light-years, creating structures that completely traverse the intergalactic medium between neighboring galaxy groups. These aren't just streams of hot gas, but coherent beams of particles accelerated to 99.99% of light speed and maintaining their collimation across distances that light takes hundreds of millennia to cross, like cosmic particle cannons operating on galactic scales. These jets accelerate material to velocities so extreme that time dilation effects become significant. The particles in these jets experience time passing more slowly than the rest of the universe due to their extreme velocities. The jets create shock waves that heat intergalactic gas to temperatures exceeding 100 million degrees, fundamentally altering the chemistry of vast cosmic regions. The luminosity of an average quasar equals approximately 1,000 times the total brightness of the Milky Way. Yet this energy originates from a region 100 million times smaller than our galaxy. It's like concentrating the light output of 1,000 major metropolitan areas into a space the size of a single city block, then maintaining that impossible brightness for geological timescales. If each star in the Milky Way were represented by a grain of sand, a quasar's energy output would be equivalent to converting every grain into a nuclear bomb and detonating them all simultaneously for millions of years. The energy density approaches the limits of what matter can produce without violating fundamental physical laws. The temperatures and pressures involved recreate conditions similar to the first moments after the Big Bang. Observations reveal that quasars can vary their brightness dramatically over timescales as short as hours. This variability proves that regions smaller than our solar system can produce luminosity superior to billions of entire galaxies. The rapid changes indicate that the energy-producing region cannot be larger than the distance light travels in the observed variability time. Think about this constraint carefully. An object that outshines billions of galaxies is varying its output on timescales shorter than a human workday. This means the entire energy-producing mechanism fits within a spacelight, can cross in a few hours. Yet it generates more power than hundreds of billions of stars combined. Quasar radiation spans the entire electromagnetic spectrum with extreme intensity, from low-energy radio waves to high-energy gamma rays capable of destroying organic molecules at distances of thousands of light-years. The broad-spectrum emission indicates multiple physical processes operating simultaneously at energy levels that exceed anything else in nature. The gamma-ray emission alone from powerful quasars can sterilize planets across vast distances. These high-energy photons can penetrate planetary atmospheres and break apart molecular bonds in DNA and other organic compounds. A nearby quasar could render entire solar systems uninhabitable, not through heating or gravitational disruption, but through pure radiation damage to biological chemistry, like cosmic power plants operating without pause. The most powerful quasars consume material equivalent to 1,000 Earth masses every second. That's roughly equivalent to devouring our entire planet, including its molten core, every second of every day for millions of years. The black hole's gravitational field organizes this infalling matter into the most efficient energy conversion system known to physics. The energy density near quasars becomes so extreme that radiation pressure alone can accelerate gas to galactic escape velocities. Material is expelled at speeds reaching 20 kilometers per second, fast enough to completely escape the gravitational pull of even the most massive galaxies. This creates galactic winds that can permanently strip gas reservoirs needed for future star formation. These outflows carry mass equivalent to hundreds of stars annually. Over millions of years of quasar activity, this represents the removal of material that could have formed billions of new stars. The quasar essentially sterilizes its host galaxy, preventing future generations of star formation by removing the raw materials necessary for stellar birth. Theoretical models indicate that quasars represent the most violent phase in galactic evolution. They likely occur during major galaxy mergers, when gravitational interactions between colliding galaxies funnel enormous quantities of gas and stars toward the central supermassive black holes. The collision provides both the trigger mechanism and the fuel supply for maximum quasar activity. During these merger events, two supermassive black holes eventually spiral toward each other. As they approach, gravitational torques reshape the surrounding stellar orbits and gas flows, creating conditions where material can overcome angular momentum barriers and fall directly into the feeding zone. The result is a cosmic feeding frenzy that can persist for millions of years. This frenzied feeding cannot continue indefinitely. Eventually, either the available material is consumed, expelled, or heated to temperatures where it cannot cool and condense onto the black hole. The quasar phase represents a self-limiting process. The very violence of the feeding eventually cuts off the food supply, causing the object to fade back to a more modest, active galactic nucleus or complete dormancy. But while this cosmic feast persists, quasars transform into the most effective destruction machines the universe has ever produced. They become capable of altering the fate of entire cosmic regions, preventing galaxy formation across volumes measured in millions of cubic light-years, and fundamentally changing the architecture of matter distribution on the largest scales. The feeding frenzy cannot last forever, but while it persists, quasars become the universe's ultimate weapons of mass destruction, capable of altering the destiny of cosmic regions larger than anything we've previously imagined. In the observable universe, there exist approximately 2 trillion galaxies, each containing hundreds of billions of stars. Yet a single quasar can outshine thousands of these galactic collections combined. To grasp this scale, consider that our Milky Way contains roughly 400 billion stars, each a nuclear furnace burning for billions of years. A powerful quasar produces more light than thousands of these stellar cities combined, all from a region smaller than our solar system. If we could somehow shrink the entire observable universe down to the size of Earth, the Milky Way would become smaller than a subatomic particle. Yet even at this impossible scale reduction, a typical quasar would still be visible as a bright point of light. This analogy illustrates how quasars achieve luminosities that transcend every intuitive understanding of cosmic brightness and energy production. Like a single candle somehow managing to illuminate an entire continent when viewed from space, quasars challenge all human intuitions about the relationship between brightness, distance, and energy output. They represent objects so powerful they remain visible across cosmic distances that require light to travel for billions of years. The very existence of quasars forced astronomers to expand their conception of what was physically possible in the universe. The most distant quasar known, J0313 1806, emitted the light we detect today when the universe was merely 670 million years old. If we compress the entire 13.8 billion year history of the cosmos into a single calendar year, this quasar was already blazing brightly on January 17th. We're observing an object that was active when the universe was still in its cosmic infancy, barely past its dark ages. To visualize this primordial era more clearly, imagine each billion years of cosmic history as 1 meter of distance. We would be observing this ancient quasar from just 67 centimeters away from the Big Bang itself, during the epoch when the first galaxies were still assembling from primordial gas clouds. The universe was so young that most of the cosmic structures we see today hadn't even begun to form. The cumulative energy output of a quasar during its active lifetime of 10 million years equals the complete annihilation of 10 million solar masses converted entirely into pure radiation. This isn't nuclear fusion converting a small fraction of mass into energy. This is the total conversion of matter equivalent to 10 million suns into electromagnetic radiation, following Einstein's E-mmc2 equation. If we could somehow capture all the energy a quasar produces in just 1 second, that amount would power the entire human civilization for 100 trillion years at our current level of energy consumption. 1 second of quasar output equals 100. 0 times longer than our species has existed, powering every electrical device, every transportation system, every industrial process humanity has ever conceived. The relativistic jets from the most powerful quasars carry kinetic energy equivalent to 1046 joules. To put this staggering number in perspective, this represents enough energy to accelerate the entire mass of Earth to 90% of light speed. These cosmic particle beams transport more kinetic energy than the gravitational binding energy that holds entire solar systems together, like rivers of pure energy flowing through the emptiness of intergalactic space. These jets influence cosmic evolution across regions spanning millions of light-years in diameter. They create shock fronts that compress gas clouds and trigger star formation in some regions, while simultaneously heating other areas to temperatures that prevent cooling and condensation. The jets literally sculpt the large-scale structure of the universe. The radiation pressure from quasars becomes so intense it can expel gas from entire galaxies. These cosmic winds travel at velocities reaching 20 kilometers per second, fast enough to escape the gravitational wells of the most massive galaxies known. The expelled material carries the chemical elements forged in stellar cores, redistributing the periodic table across cosmic distances. These galactic winds transport mass equivalent to hundreds of suns annually away from their host galaxies. Over the millions of years that quasars remain active, they remove material that could have formed billions of new stars. The winds redistribute heavy elements through volumes larger than galaxy clusters, fundamentally altering the chemical composition of vast cosmic regions. If a quasar were somehow positioned at the center of our Milky Way, replacing our relatively quiet Sagittarius A, its radiation would completely ionize the interstellar medium within a radius of 50,000 light-years. This would sterilize half of our entire galaxy, stripping electrons from atoms and creating conditions where normal chemistry becomes impossible across billions of stellar systems. The radiation environment near a galactic center quasar would be so extreme that complex molecules could not exist. Organic compounds would be instantly dissociated by the intense flux of ultraviolet and X-ray photons. Any planets within tens of thousands of light-years would have their atmospheres stripped away and their surfaces bombarded with radiation levels lethal to any conceivable form of life. Near quasars, temperatures reach billions of degrees Kelvin. At these extreme conditions, not even atoms can maintain their integrity. Matter decomposes into its fundamental constituents of isolated nuclei and free electrons. The thermal energy exceeds the binding energy that holds electrons in atomic orbitals, creating a plasma state where the normal rules of chemistry cease to apply. Like nuclear furnaces operating at temperatures that exceed the cores of the most massive stars. Quasar accretion disks recreate conditions similar to the first moments after the Big Bang. The temperature and energy density approach values that existed only in the primordial universe, when fundamental forces were still separating and matter was beginning to condense from pure energy. The energy density in quasar accretion disks exceeds 10-15 joules per cubic meter. This is equivalent to compressing the energy of 100 tons of TNT into every single cubic centimeter of space. The energy concentration is so extreme that the pressure of electromagnetic radiation becomes comparable to the gravitational forces trying to pull material toward the black hole. Magnetic fields around quasars reach intensities of 10,000 teslas. These fields are 200 million times stronger than Earth's magnetic field and powerful enough to organize plasma into enormous helical structures that channel material and energy across thousands of light years. The magnetic pressure in these regions exceeds the thermal pressure of the superheated gas. Observational evidence reveals that some quasars maintain their extreme luminosity for more than 100 million years. These represent cosmic energy machines operating continuously for geological timescales, outlasting the entire evolutionary history of complex life on Earth. They function as persistent beacons of destruction, fundamentally altering their cosmic neighborhoods for eras longer than multicellular organisms have existed on our planet. During this extended active period, a typical quasar emits more total energy than 100 trillion supernovas. But unlike stellar explosions that release their energy in brief, chaotic bursts, quasars provide controlled and directed energy output over millions of centuries. They represent sustained cosmic violence rather than momentary catastrophes. The gravitational effects near quasars become so extreme they alter the flow of time itself. Clocks run 30% slower near the event horizon compared to the outer regions of the accretion disk due to gravitational time dilation. The difference in gravitational potential creates chronological gradients where different parts of the quasar system experience time at measurably different rates. This time dilation means that processes occurring near the black hole appear to unfold in slow motion when observed from greater distances. The extreme curvature of space-time creates conditions where the fundamental nature of causality becomes distorted. Events that take minutes near the event horizon may appear to take hours when viewed from the outer edges of the accretion disk. These numbers completely transcend human experience and intuition. We're discussing energy outputs that exceed the combined nuclear arsenal of humanity by factors requiring dozens of zeros to express. The scales involved represent forces operating at the absolute limits of what the laws of physics permit in our observable universe. The magnetic field strengths approach values where quantum mechanical effects begin to influence the behavior of empty space itself. At such extreme field intensities, the vacuum becomes polarized and virtual particle pairs become real, creating exotic physics that exists nowhere else in the known cosmos except in the immediate vicinity of neutron stars and quasars. Even our most advanced theoretical physics struggles to model the complete behavior of matter under such extreme conditions. The combination of intense gravity, electromagnetic fields, relativistic velocities, and extreme temperatures creates environments where multiple exotic physical phenomena operate simultaneously. Quasars represent natural laboratories where the universe experiments with physics at its most fundamental limits. These cosmic monsters operate at energy scales that dwarf every other phenomenon we've explored. They represent the ultimate expression of gravitational energy conversion, magnetic field acceleration, and matter-energy transformation. Quasars stand at the apex of cosmic violence, operating at the theoretical maximums permitted by the fundamental forces of nature. The numbers we've discussed represent forces that operate at the absolute boundaries of what the laws of nature allow in the observable universe. Yet even these staggering energy outputs pale in comparison to the true destructive potential of quasars. Their ability not just to shine brightly, but to fundamentally alter the evolution of cosmic structure across billions of light years. Quasars are not merely the brightest objects in the universe. They represent galactic extinction machines capable of sterilizing entire cosmic regions and interrupting star formation for billions of years. They are cosmic assassins that can permanently transform vibrant star-forming environments into barren voids where nothing can ever live again. Recent research has revealed that the quasar VKJ23483054 has created a galactic desert extending 16 million light-years in radius. Within this enormous sphere of space, no galaxy can actively form new stars. This single quasar has rendered sterile a volume of space that would normally contain hundreds of actively star-forming galaxies, creating a cosmic wasteland larger than the distance to the Andromeda galaxy. Like a cosmic predator hunting within its own territory, this quasar has systematically sterilized a region of space that contains more volume than thousands of galaxies combined. The affected zone represents a sphere 32 million light-years in diameter. If placed at our location, it would encompass every galaxy in our local group and extend far beyond into the cosmic void. The ultraviolet radiation and X-rays from quasars can ionize hydrogen in gas clouds at distances reaching 50 million light-years. This ionizing radiation prevents gas from cooling and condensing into the dense clouds necessary for star formation. The radiation field is so intense it can strip electrons from atoms across distances that light takes 50 million years to traverse. Imagine a nuclear weapon that, instead of exploding once, continues detonating continuously for millions of years. This represents the temporal scale of quasar destruction in cosmic environments. Unlike stellar explosions that release energy in brief bursts, quasars maintain their devastating output for periods longer than complex life has existed on Earth. The persistence of this destruction means that quasar-affected regions cannot recover during cosmologically relevant timescales. While supernovas might sterilize local neighborhoods for thousands of years, quasars prevent star formation across cosmic volumes for millions of times longer. They create permanent exclusion zones in the universe's capacity for stellar birth. Quasar winds achieve velocities exceeding galactic escape speeds, permanently removing the fuel necessary for future generations of star formation. These cosmic hurricanes blow at 20,000 kilometers per second, fast enough to completely strip gas reservoirs from entire galaxies. Once expelled, this material cannot return. It is lost forever to intergalactic space, like cosmic vacuum cleaners operating in reverse. Quasars don't merely consume nearby material. They violently expel gases that could have fed billions of future stellar systems. The mass loss rates are so extreme that active quasars can remove more material from their host galaxies than those galaxies can gravitationally retain. Computer simulations demonstrate that galaxies hosting active quasars can have their star formation reduced by 90% during active periods. Vibrant spiral galaxies with active stellar nurseries transform into dead elliptical systems where new star formation has virtually ceased. The quasar effectively murders the galaxy's ability to create new generations of stars. This transformation represents one of the most dramatic changes possible in galactic evolution. A galaxy that might have continued forming stars for billions of years instead becomes a stellar graveyard within just a few million years of quasar activation. The change is irreversible. Once the gas is expelled or heated beyond the cooling threshold, the galaxy cannot resume normal star formation. Quasar feedback operates through two simultaneous destruction mechanisms. First, the intense radiation heats intergalactic gas to temperatures exceeding 100 million degrees, preventing it from cooling and condensing into star-forming clouds. Second, powerful winds physically expel material to distances where it cannot gravitationally return to the galaxy. ALMA telescope observations have revealed molecular winds in quasar host galaxies, expelling 1,000 solar masses of gas annually. This outflow rate exceeds the star formation rate by factors of 10. The galaxy loses potential star-forming material faster than it can convert existing material into stars. It's like a factory that throws away raw materials faster than it can manufacture products. Like cosmic wildfires, quasar jets create shock waves that propagate through the intergalactic medium. These shocks heat gas to temperatures that prevent cooling for hundreds of millions of years, creating vast bubbles of superheated matter that persist long after the quasar itself becomes inactive. The shock fronts travel at thousands of kilometers per second, carrying destruction across millions of light years. These shock-heated bubbles can persist for hundreds of millions of years after quasar activity ceases. Even when the central engine shuts down, its destructive legacy continues, preventing star formation across enormous volumes of space. The heated gas acts like a cosmic exclusion zone, maintaining temperatures too high for gravitational collapse and stellar birth. The increased metallicity observed in galaxies that have experienced quasar feedback reveals their isolation from external gas supplies. These galaxies show chemical signatures indicating they were forced to form stars using only their internal gas reserves, enriched by previous generations of stellar nucleosynthesis. They were cut off from the pristine hydrogen that normally feeds ongoing star formation. Comparative studies reveal that cosmic regions that hosted powerful quasars contain 60% fewer small galaxies than equivalent regions without historical quasar activity. This deficit represents billions of galaxies that never formed because quasar radiation and winds prevented the gravitational collapse of gas clouds that would have become stellar nurseries. The impact of quasars on cosmic evolution is so profound, they can alter matter distribution on the scales of galaxy clusters. They create permanent voids in the cosmic web, regions where normal structure formation was suppressed by their radiation and winds. These voids persist as monuments to ancient quasar destruction, billions of years after the objects responsible became dormant, like cosmic gardeners wielding chainsaws instead of pruning shears. Quasars reshape the universe's architecture by permanently eliminating entire regions of potential galaxy formation. They don't just trim cosmic structure, they clear-cut vast volumes of space, preventing any future stellar or planetary development across regions larger than galactic superclusters. The era of maximum quasar activity, occurring 1 to 3 billion years after the Big Bang, precisely coincides with the period when global star formation peaked and then began rapidly declining. This correlation suggests that quasars were directly responsible for ending the universe's most productive period of stellar birth. They terminated the cosmic renaissance of star formation. This timing indicates that quasars interrupted the golden age of cosmic star formation. The universe was transforming from a young, vibrant cosmos actively creating new stellar systems into an increasingly cold and empty space where star formation became progressively rarer. Quasars acted as cosmic population control, limiting the total number of stars that could ever form. Theoretical projections suggest that without quasar regulatory activity, the universe would contain 5 times more stars. This means potentially billions of times more planets, and by extension, billions of times more opportunities for habitable worlds and life to develop. Quasars may have fundamentally limited the cosmic potential for life by restricting stellar formation. The implications are staggering. Every quasar that blazed billions of years ago eliminated countless stellar nurseries that could have produced solar systems like ours. The reduction in star formation directly translates to fewer rocky planets, fewer opportunities for water-based chemistry, and fewer chances for life to emerge and evolve. Regional surveys comparing star formation rates in areas with and without ancient quasar activity show persistent deficits that continue to the present day. The destructive effects are not temporary. They represent permanent alterations to the universe's capacity for creating new stars and planets. Regions affected by ancient quasars remain relatively barren billions of years later. Paradoxically, the brightest objects in the universe are also responsible for making it progressively darker. Quasars represent agents of cosmic extinction operating on scales of time and space that transcend human comprehension. They are simultaneously the most luminous and most destructive phenomena in cosmic history. The brightest beacons in the cosmos function as harbingers of darkness. They illuminate vast regions of space, while simultaneously ensuring those same regions will remain forever dim. Their light travels across billions of years to reach us, carrying news of ancient destruction that shaped the cosmic environment we inherit today. This paradox reveals the fundamental duality of cosmic evolution. The same processes that create the universe's most spectacular displays of energy and light also serve as mechanisms of cosmic sterilization. Beauty and destruction operate on scales so vast, they become indistinguishable aspects of the same cosmic phenomena. Quasars represent agents of cosmic extinction operating on scales of time and space that remain unimaginable even after our journey through stellar explosions, black hole mergers, and galactic collisions. They are the universe's ultimate predators, capable of hunting and killing not just individual stars or planetary systems, but entire galactic communities across volumes measured in hundreds of millions of cubic light-years. The discovery of quasars completely revolutionized our understanding of power, scale, and destiny in the universe, revealing that the most luminous forces are also the most destructive in all of creation. This revelation forced us to confront a profound truth. Cosmic beauty and cosmic violence are not opposites, but rather different manifestations of the same fundamental processes operating at scales beyond human comprehension. These cosmic beacons serve simultaneously as landmarks of the universe's infancy and as agents of its progressive maturation. They mark the transition from a young, fertile cosmos, actively creating new stellar nurseries, to an increasingly aged and sterile universe where star formation becomes ever rarer. Quasars represent the cosmic equivalent of a forest fire that clears old growth to make way for new ecological patterns, like silent witnesses to bygone cosmic eras. The quasars we observe today have been dead for billions of years, yet their ancient light continues traveling through space, carrying detailed records of epochs of unimaginable violence that shaped the fundamental architecture of reality. We are archaeological astronomers, excavating the fossilized light of cosmic catastrophes that occurred before our solar system existed. The extreme distances to these objects mean we are literally observing cosmic archaeology. We glimpse events that molded the basic structure of the universe when it was merely a cosmic child, still learning the rules of its own evolution. These observations provide direct witness testimony to the universe's most violent and transformative period. If cosmic history were compressed into a book containing 13.8 billion pages, quasars would appear predominantly in the first billion pages. This was the era when the universe was still writing the fundamental rules of cosmic evolution, determining which structures could form and which regions would remain forever barren. The early universe was a cosmic laboratory, conducting experiments in matter, energy, and structure formation. During this primordial epoch, the universe was testing the limits of what physical laws would permit. Supermassive black holes were growing to unprecedented sizes. Galaxies were colliding and merging with frequencies impossible in today's more settled cosmos, and energy densities approached values not seen since the immediate aftermath of the Big Bang itself. The absence of quasars in our local cosmic neighborhood suggests that this phase of galactic destruction has largely passed. We live in the aftermath of that cosmic storm, surrounded by the energetic fossils of ancient violence in the form of dormant, supermassive black holes that once powered the universe's most destructive machines. Like extinct volcanoes that shaped terrestrial landscapes before falling silent. The central black holes in modern galaxies are the quiet remnants of an era when creation and destruction operated on titanic scales. These gravitational monsters consumed matter equivalent to billions of stars during their active phases, then settled into the cosmic equivalent of hibernation as their fuel supplies were exhausted or expelled. The total energy radiated by all quasars throughout cosmic history equals approximately the complete annihilation of 1011 solar masses converted entirely into radiation. This represents the largest mass-to-energy conversion event since the Big Bang itself. The cumulative quasar output approaches the energy scale of the primordial universe, demonstrating how these objects briefly recreated conditions similar to cosmic genesis. This ancient quasar radiation persists today as part of the cosmic background, contributing to the universal heating that prevents space from cooling to absolute zero. Every cubic centimeter of seemingly empty space contains photons that originated in quasar accretion disks billions of years ago. The universe still glows faintly with the accumulated light of ancient cosmic violence. Paradoxically, the most violent objects in cosmic history were also responsible for establishing the conditions that allowed stable galaxies like the Milky Way to form and persist. Without quasar regulation, primitive galaxies would have grown uncontrollably into unstable giants, incapable of maintaining ordered star formation for the billions of years required to evolve complex chemistry and life. The feedback mechanisms operated like cosmic population control. Quasars prevented the universe from producing too many massive galaxies that would have quickly exhausted their star-forming material and become sterile much earlier than observed. They enforced a cosmic speed limit on galactic growth that allowed smaller, more stable systems to develop gradually. Without this regulatory activity, early galaxies would have undergone runaway growth. They would have become so massive and turbulent that gravitational interactions would have prevented the formation of stable stellar nurseries. The chaotic environment would have been hostile to the gradual chemical evolution necessary for rocky planets and biological chemistry. The heavy elements essential for rocky planets and life, carbon, oxygen, silicon, iron, were partially distributed throughout the cosmos by violent quasar winds. These cosmic storms carried the products of stellar nucleosynthesis across intergalactic distances, seeding future star-forming regions with the chemical ingredients necessary for terrestrial planets and complex chemistry. Like cosmic seed spreaders, quasars helped enrich the intergalactic medium with materials produced in the nuclear cores of the first generation of massive stars. Without this distribution mechanism, heavy elements would have remained trapped in the galaxies where they formed, preventing the chemical evolution of later stellar generations and planetary systems. Our own existence depends indirectly on the ancient era of quasar activity. Without their regulatory influence, the Milky Way might have become too massive and turbulent to permit the formation of our solar system. The relatively calm galactic environment that allowed our Sun to form and maintain stable planetary orbits for billions of years exists because quasars prevented excessive galactic growth. The chemical composition of our solar system bears the signature of this ancient cosmic violence. Many of the heavy elements in our bodies and our planet were processed through multiple generations of stellar evolution and distributed by galactic winds powered by quasar activity. We are literally composed of material that passed through cosmic storms billions of years ago. Observing quasars with our most powerful telescopes represents one of the few ways humanity can directly witness events that occurred billions of years before Earth's formation. These observations allow us to study cosmic processes that shaped the fundamental structure of the universe during epochs when physical conditions were radically different from today's relatively calm cosmos. Each photon of quasar light reaching our detectors has traveled through the expanding universe for longer than our entire galaxy has existed. These ancient light particles carry encoded information about epochs unimaginably remote in time, delivering news of cosmic events that occurred when the universe contained no galaxies resembling any we see today. The journey of these photons spans cosmological timescales that challenge human comprehension. They began their voyage when the universe was young and violent, traveled through cosmic voids that expanded during their trillion-year journey, and finally arrived at Earth, carrying pristine information about conditions in the primordial cosmos. The technology required to detect these ancient signals, from radio telescopes to space-based X-ray detectors, represents some of the greatest engineering achievements in human history. These instruments must capture photons that have traveled billions of light years, while maintaining enough sensitivity to measure spectral details that reveal the physics of distant cosmic engines. Through studying quasars, humanity has developed profound understanding of black hole physics, general relativity, galactic evolution, and the fundamental nature of space-time, curved by extreme gravity. These observations have confirmed theoretical predictions about the most extreme environments possible in the universe, validating our mathematical descriptions of reality at its most fundamental level. Radio interferometry networks spanning continents work together to resolve details of quasar jets extending across thousands of light years. X-ray satellites detect the signatures of matter being torn apart by gravitational forces 1 billion times stronger than anything experienced on Earth. Optical surveys catalog millions of these ancient objects, mapping the distribution of cosmic violence across space and time. Quasars teach us cosmic humility by revealing that the most powerful forces in the universe operate on scales completely beyond human experience. Yet these incomprehensibly distant and ancient objects continue to govern our cosmic destiny through their role in shaping the large-scale structure and chemical evolution of the universe we inhabit today. The energies we've discussed transcend every scale of human technology and natural terrestrial phenomena. A single quasar produces more power than humanity could generate by converting every atom on Earth into pure energy. Yet we can detect and study these objects across billions of light years, demonstrating the remarkable reach of human curiosity and ingenuity. This journey of discovery, from the first detection of mysterious radio signals in the 1950s to our current understanding of galactic extinction machines, represents one of humanity's greatest intellectual achievements. We have successfully decoded signals from the most distant and powerful objects in the universe, revealing their role in cosmic evolution through pure scientific investigation. The progression from puzzling observations to theoretical understanding showcases the cumulative power of human knowledge. Generations of astronomers, physicists, and engineers collaborated across decades to transform inexplicable radio noise into comprehensive understanding of cosmic evolution. This represents science at its most triumphant. This journey of discovery represents one of humanity's greatest intellectual achievements, demonstrating our species' remarkable ability to decode the universe's most distant and violent phenomena through careful observation, mathematical analysis, and technological innovation. Yet, perhaps the most profound lesson from quasars lies not in their cosmic significance, but in what they reveal about our own extraordinary position in the vast theater of space and time. Confronted with the devastating scale of quasar destruction, we are forced to acknowledge a profound reality. We inhabit a universe shaped by forces that completely transcend our capacity for influence or control. The energies we've explored operate on scales so vast that all of human civilization represents less than a grain of sand compared to a hurricane. Yet somehow, against all odds, we exist, and have developed the ability to comprehend these cosmic giants that dwarf our entire galactic neighborhood. Our galaxy, the Milky Way, exists in its current stable form precisely because it survived the era of quasar dominance. We live on what amounts to a cosmic island of stability in a universe that once knew unimaginable violence. Our galactic home represents one of the fortunate survivors of an epoch when cosmic destruction machines routinely sterilized entire regions of space, leaving behind vast cosmic deserts where no stars could ever form again. The survival of our galaxy represents an extraordinary stroke of cosmic fortune. During the universe's violent youth, when quasars were common and active, countless other stellar communities were destroyed before they could develop the stable environments necessary for life. We inhabit one of the cosmic safe havens that managed to avoid complete sterilization during the era of maximum galactic destruction. Like survivors of a cosmic shipwreck, we have found refuge in a specific time and place where the galactic extinction machines have exhausted their fuel and fallen dormant. The supermassive black hole at our galaxy's center, Sagittarius A, consumed its available material billions of years ago and now sleeps quietly, allowing our spiral galaxy to maintain the peaceful stellar nurseries where our sun was born 4.6 billion years ago. The dormancy of Sagittarius A represents more than just local tranquility. It symbolizes the end of an era when cosmic violence operated on scales that could reshape the fundamental architecture of the universe. Our galactic center now produces only occasional flickers of activity, gentle reminders of the epoch when similar objects across the cosmos blazed with the power of thousands of galaxies combined. Earth orbits a middle-aged star in a tranquil galaxy during a cosmically peaceful era. This convergence of circumstances is extraordinarily rare in universal history. We exist during the calm after the cosmic storm, in a galaxy that avoided destruction, around a star stable enough to sustain life for billions of years. On a planet positioned perfectly within the habitable zone, the probability of this confluence is almost vanishingly small. If we compressed all of cosmic history into a single 24-hour day, the entire existence of humanity would occupy less than the final millisecond before midnight. Meanwhile, the era of maximum quasar activity dominated the early morning hours when the universe was young and violent. We are latecomers to a cosmos that has already experienced its most dramatic and destructive phase, arriving only after the cosmic storms had subsided. Our technological civilization developed during the past 13.7 billion years of relative galactic calm. This period of stability was only possible after quasars ceased their destructive activity in our local cosmic neighborhood. We evolved during cosmic old age, when the universe had settled into patterns that could sustain complex chemistry and biological evolution for the geological timescales required for intelligence to emerge. The timing of our emergence is remarkable when considered against cosmic scales. If humanity had somehow evolved during the quasar epoch billions of years ago, our night sky would have blazed with objects brighter than our moon, while deadly radiation would have prevented complex chemistry from developing anywhere in our galactic region. We exist only because we arrived after the universe's violent phase had passed. The same violence that made quasars so destructive paradoxically created the conditions necessary for life to emerge billions of years later. The regulatory feedback that prevented runaway galactic growth also established the stable galactic environments required for gradual stellar evolution and planetary formation. Cosmic destruction and cosmic creation are intimately linked processes operating on timescales that span cosmic ages, like involuntary cosmic gardeners. quasars pruned the young and chaotic universe. They prevented the formation of galaxies so massive and turbulent that stable stellar ecosystems could never develop. By limiting galactic growth and redistributing matter across cosmic distances, they allowed regions like our galactic neighborhood to evolve into stable stellar communities capable of sustaining life for billions of years. The gardening analogy extends to chemical enrichment as well. Quasar winds carried the products of stellar nucleosynthesis across intergalactic space, seeding future star-forming regions with the heavy elements necessary for rocky planets and biological chemistry. Without this cosmic distribution system, the materials essential for life would have remained trapped in their galaxies of origin. The chemistry of life on Earth directly depends on heavy elements forged in massive stars and distributed throughout the cosmos by violent quasar winds billions of years ago. The carbon in our DNA, the oxygen we breathe, the iron in our blood, and the calcium in our bones were all processed through multiple generations of stellar evolution and scattered by cosmic storms that preceded our solar system's formation by eons. Every carbon atom in your body, every oxygen molecule you breathe, may contain material expelled from a distant galaxy by quasar radiation during the universe's violent youth. We are literally composed of cosmic debris from ancient galactic destruction events. The elements that make life possible traveled billions of light years through space before eventually condensing into the planets and organisms of our solar system. The cosmic recycling process that created us operated across scales of time and distance that challenge human comprehension. Materials forged in the nuclear cores of massive stars billions of years ago were ejected by supernova explosions, caught up in quasar winds, transported across intergalactic space, and eventually incorporated into the gas clouds that collapsed to form our sun and planets. Our ability to observe and understand quasars represents an extraordinary moment in cosmic history. For the first time since the universe began, matter has organized itself into structures complex enough to comprehend the violent processes that shaped cosmic evolution. The universe has developed consciousness capable of contemplating its own dramatic past and understanding the mechanisms that created the conditions for awareness itself. Through telescopes and detectors, humanity has become an eyewitness to events that preceded our existence by geological eras. We can observe cosmic violence that occurred when the universe contained no galaxies resembling anything we see today. Our instruments allow us to connect our tranquil present with the turbulent cosmic past that created the conditions for our existence through billions of years of cosmic evolution. The technology required for these observations represents some of humanity's most remarkable achievements. Radio telescopes that can detect signals from objects billions of light years away. X-ray satellites that operate above Earth's atmosphere to capture high-energy radiation from ancient cosmic violence. And optical surveys that catalog millions of these distant destroyers across vast volumes of space and time. The discovery of quasars teaches us that we live in a universe of extreme contrasts. Regions of absolute calm coexist with destruction machines capable of sterilizing millions of cubic light-years of space. The universe contains both the gentle stellar nurseries where our sun formed and cosmic engines powerful enough to prevent galaxy formation across volumes larger than galactic superclusters. This cosmic perspective fundamentally transforms our understanding of rarity and preciousness. We are products of an improbable sequence of events that began with galactic violence and culminated in habitable planets. The path from quasar-dominated chaos to stable planetary systems required an extraordinary convergence of cosmic circumstances occurring over billions of years of careful cosmic evolution. The temporal scales involved in quasar evolution remind us that even the most powerful cosmic phenomena are transient. These engines of destruction operate for millions of years, but then remain dormant for billions of years thereafter. Their violence, however extreme, represents temporary phases in cosmic evolution rather than permanent features of the universe's architecture. Our brief, conscious existence coincides with a unique historical period when the echoes of the quasar era remain detectable. But their destructive consequences have ceased affecting our local cosmic region. We live during a cosmic sweet spot when we can study the remnants of ancient violence without experiencing its direct effects. We are cosmic archaeologists, examining the fossilized remains of universal destruction. Human technology, despite all its sophistication, manipulates energies that are billions of trillions of times smaller than the output of an average quasar. This comparison illustrates the humility required when confronting cosmic forces. Our most powerful nuclear weapons represent less energy than a quasar produces in the time it takes light to cross a single atom. We are cosmic children, playing with toys while contemplating forces that shaped galaxies, yet our unique capacity to understand, name, and quantify these phenomena represents something extraordinary in the universe. Common matter has somehow organized itself into patterns complex enough to become conscious of the dramatic history that created it. The universe has evolved the ability to study itself through the emergence of scientific intelligence capable of decoding cosmic violence across billions of years and light years. The development of consciousness capable of cosmic comprehension may be one of the rarest phenomena in the universe. While quasar violence was common during the universe's youth, the emergence of intelligence capable of understanding that violence appears to be extraordinarily rare. We may represent one of the few examples of matter achieving self-awareness on cosmic scales. Quasars teach us that being small does not mean being insignificant. We are rare products of 13.8 billion years of cosmic evolution that included both creation and destruction on unimaginable scales. Our existence required the universe to navigate between cosmic extremes, enough violence to distribute heavy elements and regulate galactic growth, but not so much as to prevent stable stellar evolution. The formation of our solar system required a delicate balance of cosmic circumstances. Too much nearby quasar activity would have prevented our galaxy from forming stable stellar nurseries. Too little would have left us in a universe dominated by massive, short-lived galaxies incapable of sustaining the gradual evolution necessary for life. We exist in a cosmic Goldilocks zone of violence and tranquility. Our planet's habitability depends on cosmic processes that operated billions of years before Earth existed. The regulation of galactic growth by ancient quasars, the distribution of heavy elements by cosmic winds, and the eventual dormancy of local destruction machines all contributed to creating conditions where rocky planets could form and sustain liquid water for geological timescales. The rarity of our situation becomes more apparent when we consider the cosmic violence we've explored. The universe spent its early eons dominated by destruction machines capable of preventing life from ever emerging across vast regions of space. We inhabit one of the relatively few cosmic neighborhoods that survived this violent phase and achieved the stability necessary for biological evolution. As we contemplate the true scale of quasars, we find our perspective simultaneously humbled and elevated. We are minuscule in the face of cosmic immensity, but precious beyond measure for our unique capacity to understand and appreciate the vastness that created us. And that brings us to the end of our journey for today. If you're still awake after all this, I guess the video must really be good. If you enjoyed it, I'd truly appreciate it if you could leave a like and subscribe for more videos like this. To keep the experience going, click and watch the next video that's popping up on your screen. I'll see you there. Until next time.